coming back. So let's continue the second half. Okay, until here, we learned the complicated way, I mean, many steps to attach frame and derive the DH parameter that represent the link. So we still don't know how can we use the DH parameter of the link to obtain the goals that we want. On this slide, the detail is from our last time lecture, and at that time we mentioned about the homogeneous transform. The homogeneous transform is derived from the idea that, hey, if we have the global coordinate frame A, and if we have another moving frame B that is connected to some moving object, and the frame B is observing a particle, so the position of that particle with respect to the frame B is described by the position vector with respect to the frame B. And we also know that the origin of frame B can be described by the position vector with respect to the global frame A. And in order to describe the position of that object with respect to the frame A, the idea is we need to write down the position vector of the origin of the frame B with respect to the frame A. And then we know the position of B, position of the particle with respect to the frame B. And by multiplying this position vector with the rotational metric of the frame B with respect to the frame A, we can have the relationship between the position in the global frame of an object from the position vector that we know, the position of the object with respect to the frame B. But instead of having the 3×1 vector instead of have the vector 3×1, have rotational metric 3×3 multiplied by the vector 3×1 and plus the vector 3×1. Instead of doing this operation, we see the advantage of composing the homogeneous transform, which is the 4×4 metric. And the homogeneous transform will combine the effect of the rotational metric. Combine the effect of the rotational metric and combine the position vector of the B origin with respect to the global frame A. And finally, we can relate the position that observed in the frame B and the position that observed in the global frame A. And also we know that maybe we can find the inverse. We also derive the inverse of the homogeneous transform. And for example, if we know this, and if we just only want to know the difference between the transform from D to with respect to B, for example, the idea is we may just only multiply this with the inverse of this in front of the TBU, and we have TCB and TDC. Just like this. I mean, if you just multiply the inverse in front of this set, yeah, this one will cancel, and finally you will have only the relationship between the two frames instead of three frames. So it's very useful to use the homogeneous transform. It's convenient. And yet one more thing that we should still remember is how to compose the rotational metric. To compose the rotational metric, what we need to do is, hey, if we have the frame XA, YA, and ZA, what's gonna happen if we rotate the frame from A to frame B about the Z axis only? What's gonna happen? If we rotate it, for example, with the angle theta, if we rotate the frame from A to B with the angle theta, how can we derive the rotational metric about the Z direction with the angle of rotation theta? We need to use the vector xb to obtain the dot product with xa, ya, and za, right? xb dot xa, xb dot xa will be the magnitude of xb multiplied by magnitude of the unit vector xa multiplied by the cosine of the angle between xb and xa. And we know that xb and xa are unit vector, so the magnitude is equal to 1. So the dot product between unit vector will result in the cosine of magnitude. So xa dot xb here will be cosine theta. xb dot ya, if this angle is theta, this one angle between x and y are 90 degrees. This angle will be 90 degrees minus theta. So the direction between xb and ya, the direction between xb and ya will be cosine of 90 minus theta. And the dot product of xb and za, xb always normal to the za, so cosine 90 degree is 0. How about YB to XA? YB, I'm sorry, this should be YB. YB to XA. The dot product of YB to XA, cosine of YB to XA, it will be minus. Okay, if you want to obtain the angle between the YB and XA, it's gonna be cosine of 90 degree plus the theta, the angle between YB and XA. The angle between the YB and YA will be cosine theta. And the angle between YB and CA will be 90 degree. Cosine 90 will become 0. How about the Z of the B? CB XA 90 degree. CB YA 90 degree. And CB and CA have 0 degree. Cosine 0 is equal to 1. So this is how we compose the rotational metric. So the step, the homogeneous transform that show the relationship between maybe frame 1 to frame 0. From frame 1 to frame 0, we derive the Dynamit-Hartenberg parameter. We know the link length, link twist, offset, and angle. The meaning of the parameter is come from here. For the link twist, for the joint angle, we rotate about the z-axis with the angle theta. Then we translate in the z-axis with the distance d. Then we translate in the x-axis with the distance a. Then we rotate the frame with the twist alpha from the frame I-1, to the frame I. The process that we did is we firstly rotate about the z-axis with the angle theta. We translate in the z-axis with the distance d. We translate in the x-axis with the distance a. The x-axis means the x-axis after it already rotated by theta. And the frame I is the effect of the twist angle alpha again. So if we want to describe the frame I with respect to the frame I-1, the process we need to do is here we need to rotate about the z-axis with the angle theta. We translate in the z-axis with the offset, and then we translate in the x-axis with the distance link length a, and then we twist with the angle alpha. We do 4 processes before we transform from the frame 0 to frame 1, or from the frame I-1 to frame I. We need to perform 4 steps. So what is the corresponding homogeneous transform of each step? If we rotate about z-axis with the angle theta, the rotational metric will be cosine and cosine of 90 plus theta will be minus psi, and cosine of 90 subtract by theta will be psi. Okay, these are the same. The rotational metric, when we rotate about the z-axis with the angle theta, will be cosine and minus psi and psi and 0, 0, 1, 0, 0. This is the rotational metric. How about the position change? When we just rotate, the frame with the angle, the frame origin doesn't change. So the P I origin with respect to I minus 1, the position doesn't change. The position vector will be 0. But to compose the homogeneous transform, we know that we have the rotational metric, we have PB origin with respect to A, and we have 0, 0, 0, and we have 1. So we have 0, 0, 0, and have 1. And this is the rotational metric. And this is the P I origin with respect to the frame I. So this is the effect of the rotation about the z-axis. Okay, how about the effect of translation in z-axis? With the translation, the direction of the move frame and the original frame doesn't change. So if it's in the same direction, if the direction doesn't change, XA and XB are in the same direction. YA and YB are in the same direction. And the cosine product, the dot product, will equal to 1 if it doesn't change the direction. But XBYA will have 90 degrees. The other component will have 90 degree difference, so other component will be 0, 0. For the rotational metric, when it's not rotated. So it means the rotational metric for translation, it will be 0, 0, like this. And you have 0, 0, 0, and have 1. How about the position change? The PI origin with respect to the frame I minus 1. If you translate in the z-axis with the distance d. So what we have here is we have d in the z direction, only this. For this, you will try by yourself to obtain the translation in the x-axis, only pure translation. So the rotational metric will be like this. The rotational metric have 0, 0, 0, and 1. And the translation in x-axis, we have A, I. the theta of the frame I, DI, AI. Okay. The rotation about the x-axis. The rotation about the x-axis. We have x, y, and z. The rotation about the x-axis with the angle alpha, which means the frame B, xb, still be the same, but the y, b, will change the angle, the cb will change the angle, change with the angle alpha, So when we need to compose the rotation metric, we use the same idea. We need to obtain the dot product of each component. You will recheck by yourself, but for me, it will be like this. And the translation for the pure rotation, the translation, we doesn't change the origin of the frame. So the position vector will be 0 like this. And just when we perform, when you obtain the vector, the product of the metric, you may obtain the product of this first and product of this, and you make the product of the metric again. The finalized relationship is this. It means that the homogeneous transform that refer the frame I to the frame I minus 1 can be written in the metric of the parameter joint angle, the link width, the offset, and the link length, like here. You can see that for the orientation, it only depends on the angle, twist and the angle, the twist and the angle. But for the position is the effect of the link length and the joint offset, and also the joint angle. And this is the homogeneous transform that relates the neighboring frame. How about the other frame? Yeah, we know that for the neighboring frame, the homogeneous transform is described by this metric. We derive the DH parameter. We derive the DH parameter of each link, and yet for the link 1, you can compose the homogeneous transform that relate the frame 1 with frame 0. For the parameter of the link 2, you can create the homogeneous transform of link 2 with respect to the link 1, and also for the link 3. So yes, the link length, the link twist, and the joint angle, the first component is the theta, right? So the theta is the theta 1. How about here? Cosine alpha. Alpha is 90 degrees. Cosine of 90 degrees will be 0. So cosine 90 degrees will be 0. Sine of 90 degrees is equal to 1. Sine of 90 degrees is equal to 1. So we have only sine theta. and minus cosine theta 1 here. The link length of the first link is equal to R. The link length is equal to R. The cosine theta 1, sine theta 1 is here. And 0 sine of 90 degree is 1. Cosine of 90 degree is 0. The offset 0. And here we can compose the homogeneous transform that relate the frame 1 to frame 0. How about to relate frame 2 to frame 1? We use the parameter of the second link. Yes, cosine and sine of theta 2. The link twist is equal to 0. Link twist is equal to 0. It means cosine 0 is equal to 1, right? And we have theta 2. Sine of 0 is equal to 0. Sine 0 equal to 0. Cosine 0 is equal to 1. And the link length is L1. Cosine theta, sine theta. Offset 0. Offset 0. And 0, 0, 1. For the third homogeneous transform that relate the frame 3 to frame 2, we have the same pattern of the parameter. So the metric also has the same pattern. Now we can relate the frame 1 to frame 0, frame 2 to frame 1, frame 3 to frame 2. Yeah, we know that the total homogeneous transform is the product of the component of the homogeneous transform that relate the neighboring frame. So yes, when we obtain the metric product of these three metrics, if you obtain the metric product of these three metrics, the result will relate the frame 3 to frame 0. So what is the meaning by the relate frame T to the frame 0? This vector will be the position of the frame T origin with respect to frame 0. This vector 3 to 1. This vector 3 to 1 will relate the origin of the frame T with respect to frame 0 in the XYZ direction. Does that make sense? If you see, before seeing the big picture, let's consider only this. Let's consider only this. The frame 0, X0, Y0, C0, the frame 1, the frame 1 is put somewhere, origin of the frame 1 is put somewhere far from the frame 0 with the radius r, and the angle between the frame 1 and frame 0 is theta 1. So the origin of the frame 0, no, the origin of the frame 1 the origin of the frame 1 that relate to the frame 0, the x component will be r cosine theta 1, this one. The y component will be r sine theta 1. The z component of the origin of the frame 1 with respect to the frame 0, the z origin, the z component will be 0. If you want to relate the frame 2 to frame 1, if you want to relate the frame 2 to frame 1 has C1, have X, and has Y. And the frame 2, the origin of the frame 2, you know that the origin of the frame 2 has the distance from the frame 1 by the length the length should be, sorry, the length is L1. The length is L1, okay? So it means that this length is L1, and the O2 with respect to the origin of the frame 1 have the distance, the length L1, and the frame 2 rotate from the frame 1 with the angle theta 2. Does that make sense that when we write the origin of the frame 2 with respect to the frame 1, we have L cosine theta 2, we have L sine theta 2 for the y component, and the origin of frame 2 has the 0 in the z component of the frame 1. So for the subsystem, for the subframe, the relationship between the neighboring frame is true for the P1 origin with respect to frame 0. And it's also true for the P frame 2 origin with respect to frame 1. You may consider it in the same way for the frame 3 to check the P of frame T origin with respect to frame 2. How about for the big picture, for the total? Is it true that the position of the frame 3 origin, with respect to the frame O? So if you see the it seems like if you look from the top view, you're gonna see x0 and y0, and then we have one long arm with the radius and with the link, this link, you have radius r, you have L1 and you have L2. And of course, it rotates with the theta 1. And the L1, if the L1 change the direction by the theta 2 and theta 3, if you see in this direction, it seems like you have the radius r, and you have the L1 with the angle theta 2, and you have the L2 with the angle theta 3. So the projection to here, the projection is the distance from here to here. You will have the projection length of r plus L1 cosine theta 2 plus L2 cosine theta 2, 3. Cosine theta 2, 3, the meaning of C theta 2, 3 is cosine of theta 2 plus theta 3, okay? C theta 2 is mean cosine of theta 2. C theta 2t is cosine of theta 2 plus theta 3. So the projection length is here. In order to find the component in x direction and in y direction, it needs to be the projection length multiplied by cosine theta 1 and the projection length multiplied by sine of theta 1. So it's here. The projection length is in the bracket. The projection length is in the bracket. And multiplied by the cosine component for the x position, multiplied by the sine component for the y position. How about the z position? The z position. So this length is just equal to L1 sine theta 2 plus L2 sine of theta 2 plus theta 3. So this is the position in the z direction. So of course, if the robot is not that much complicated like this, you may obtain the forward kinematic by the method we learned today, or you will just check the projection of the dimension like here, the simple way to do. Don't need to compute the metric. You can obtain the forward kinematic. But for some industrial robot that has maybe 6 degrees of freedom and it's a lot more complicated, and maybe if you don't want to solve it by hand, you just compute the metric of each homogeneous transform and put everything in the computer program. It's a lot helpful for a bigger number of degree of freedom. But by the way, by understanding the physical meaning, you can cross-check your answer of the metric by this. So actually, that's almost all for today. This exercise, you will do it by yourself, and next week we will come to look about this and make the explanation again. The exercise is similar to what we learned in the class. We have the robot, the Planar level robot. It means we have first level joint, second level joint, and third level joint on frame, on plane. All the joints are on the same plane. And you need to attach frame on the robot, obtain the table of the H parameter, try to find the homogeneous transform of each link by using this metric, and then when you find the product of the metric, you can get the forward kinematic of the robot. These two pictures are the equivalent system. I mean, we have the floor, and we put a motor by connecting the stator of the motor to the floor, and the rotor of the motor is here, and you connect the second motor, connect the stator of the second motor to this link, and the rotor of the motor is continue, and you put another motor by connect the stator here and continue to the end effector. So try to assign the frame and obtain the DH parameter, construct the metric of homogeneous transform, and check the forward kinematic. From next week, we will review this example again, and we will provide a few more examples to make you understand how to attach frame and how to derive the parameter. I think the challenge is how to attach frame and find the correct value of the parameter. For the homogeneous transform and forward kinematic is the straightforward way. After you obtain the correct parameter, it's not going to be a problem to obtain the homogeneous transform. This week, we only talk about the revolute joint. Next week, we will learn how to assign frame for the prismatic joint. It's a little more complicated and require understanding. So please review today content, and we will continue on next time. Today I record the class, and maybe tonight I will receive the information for the class record. In general, I always share the link to access the record class with Gong. So maybe from tomorrow morning, you may ask Gong to about the link to the Zoom record. Okay. Do you have any question?
No ครับ
เฮ้ยสู้ๆมันแมทเยอะกว่ามันยากหน่อย
ยากครับอาจารย์
ลองไปค่อยๆดูรีวิวเรคคอร์ดแล้วกันแล้วลองเขียนตามดูน่าจะเข้าใจแหละครับโอเควันนี้ไม่มีอะไรแล้ว